For this lab, I rolled a marker on a horizontal surface in a straight line to observe an object in constant velocity. The idea of constant velocity is noted in Newton's second law, in which states that if all the forces are balanced, as in the net forces acting on the object is totaling 0 newtons, then the acceleration of that object is 0 meters per second squared, and thus the object is going in a constant velocity. This can be seen in the experiment as I was aiming for the marker to move in a straight line at a constant velocity. And so here's just a screenshot of my experiment where I pushed the marker. I used tracker to track the time and position of the moving marker. As seen in the picture on the left, I put my origin at the right side of the table and pushed the marker towards the left. The movement is positioned along the negative x-axis as well, which I provided a graph next to the screenshot so that this can be seen. The yellow arrow indicates the direction in which I pushed, which is oriented on the negative x-axis. If I were to have pushed the marker from left to right, in the positive x-axis, which is represented in the black arrow, my data points the numbers would have still been the same, just they would be positive instead of negative. The constant velocity would also stay the same as well number-wise, but it would just not be negative and it would be positive due to the fact that velocity measures speed and direction, and pushing the marker from left to right would be in the positive x direction, so that's why the numbers would change negative positive wise. At the bottom, you can see I started recording the actual time a bit after the marker started moving, so that the force of the push to get the marker going is not recorded within my data. The initial push of the marker caused the marker to speed up from rest, which is not constant velocity, as the velocity changes from 0 to around like negative 1.78 meters per second. So then after I put in the timestamps and positions of the markers, I used GlowScript, the GlowScript application, to input the initial conditions plus some more lines of code to update my velocity and position. I ended up with the data points as you can see on the right side. So after collecting all this data, I inputted it into a graph to compare the experimental data and the predicted data I got from GlowScript. Since velocity is the slope of position versus time graph, I used a position versus time graph to compare the slopes of my experimental data versus the predicted data, as in I wanted to look at the velocities. So the experimental line is fairly accurate starting at the beginning, and then after a while the data points start differing greatly from the predicted line. In the end, the slope of the observed experimental line is less than the slope of the predicted line. And according to Newton's law, constant velocity occurs when the acceleration is 0 meters per second squared and the net force is 0 newtons. But my experiment had several factors that may have impacted the state of the marker, and thus the acceleration and net force just may not have been completely 0. The experimental line may differ due to human errors as well, as I didn't move the marker straight enough, or the surface just may have been a little tilted, causing the marker to change direction a little bit. Because of the potential tilt of the marker's direction, the marker would then accelerate, as Newton's second law states that acceleration happens as a result of forces pushing on the object to change direction, which brings the object out of constant velocity as velocity is changing, and as velocity also measures speed and direction, if the direction changes, the velocity also changes, which then means it's accelerating. And so the changing of the velocity of the marker means that it, in fact, was accelerating, and therefore the net force was not 0 and it wasn't in a constant velocity at some parts of the experiment. Friction was also not taken into account, and instead we assumed it to be 0 or to just not be present. It is not possible for me to say that friction was the only force acting on the object during this time, as there could have been way more forces acting on it to impact F net. Because of such forces, my marker may have been slowed down, and thus that explains why the slope of the experimental line and the slope represents the velocity is a lot smaller than the slope of the predicted line, which is bigger. And as you can see in the picture at the bottom, that just shows that velocity does in fact change after there is a turn. In all, the experiment helps visualize Newton's second law by attempting to see an object in motion staying constant velocity with a net force of 0 newtons. The predicted model with the velocity of the marker showed what the marker's velocity and position should have been, if not for the human errors and other forces such as friction, which was assumed to be 0, which impacted the F net and the velocity in total. The ending results that's why I differed from the predicted model due to these forces and these errors. To get better results, I would have included all the known forces acting on the marker to just create a more representable prediction.